Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at a very challenging integral which gave me sleepless nights to be able to solve. So this is from MIT Integration B contest. I don't know the year. This question was actually proposed to me by a certain student who is preparing for the MIT examination. So I had to take my time, solve the integral, and here is the solution, my proposed solution I'm going to be giving you guys. All right, so if you are an advanced level student who offers further maths, then I would love you to really take your time in understanding the steps I'm going to be giving out. This might be a little bit complicated for a pure math student who does not offer further maths, but anyways, by the end of the video you're going to see how simplified the integral can be. But nevertheless, I'm going to be introducing to you guys some integration techniques that are very important. All right, so for those of you who are joining us for the first time, endeavor to subscribe to the channel, turn on your notifications so that whenever subsequent videos are uploaded, you'll be notified to come and watch. If you have been there from the beginning, we thank you very much for your subscription, your love, and your support. Endeavor to share the video at the end. You comment your worries if you have any difficulty in the comment section. You like the video and you subscribe to the channel. All right, so without wasting much of your time, let us get started. All right, so I'll take my time, okay, to really explain to you guys detailedly how I was able to come out with the solution to this problem. It was not very easy. Such integrals requires a lot of thinking, a lot of manipulations, so stay with me. All right, so my integral has been given to me. So first thing I realized my integral is that I can easily deal with a polynomial function and a Napierian logarithm function, but when I find a square root function, it becomes complicated. Okay, or I can easily deal with a polynomial function and a square root function, but when I find a Napierian logarithm function, it becomes complicated to deal with the three functions at the same time. So in this method, because I actually developed two methods to solve this problem, but in this video I'll just detailedly explain one of the methods. If you're interested in knowing the other method, you comment in the comment section that you're interested in the other method. So in this method I decided to make a u substitution so I can easily get rid of the square root. And to get rid of the square root, we need that the argument of the square root has to be a perfect square. That is why I'm letting what is inside the square root to be x squared, so that the square root of x squared will just give us x because it is already in a positive interval. Now in the next method, that is in the second method, I try to get rid of rather the ln of pi t minus 1 where I did a substitution. All right, so I cannot deal with these three functions at the same time, so I'll try to get rid of one of the functions, then I work with the other two functions. So I'll let x squared to be equal to pi to the power t minus 1. Okay, now I am changing variable, so everything in terms of t will be converted to be in terms of x. So you realize that the bounds are going to be changed, the t is going to be changed, anything concerning t will now be in terms of x. That's the very first thing we have to do. So my u substitution or my x substitution is x squared equal to pi to the power t minus 1. Now we have to, because we have to differentiate and get the t, all right, and we write the t in terms of the x. So if I differentiate both sides, the left hand side will be easy to differentiate because I'll just have 2x dx. Okay, now to differentiate the right hand side, when I differentiate 1, I get 0 because 1 is a constant. Now when I differentiate pi to the power t, it's equivalent to differentiating a constant raised to the power t, and generally if I differentiate a to the power t, I'm going to get a to the power t times the ln of a. The proof is very basic, so you can try that by yourself. Okay, by just letting y to be equal to a to the power t, we take ln on both sides, then we differentiate both sides, then you replace back what y is at the end of the day. You're going to have that the differential, the first derivative of a to the power t is always equal to a to the power t ln a, where a is a positive constant. So from here, if we differentiate pi to the power t, we are going to have pi to the power t times the ln of pi. Once we differentiate -1, we get 0 because it is a constant. So doing that, left hand side derivative gives us 2x dx, right hand side it gives us pi to the power t times the ln of pi dt, because I'm differentiating with respect to t. Okay, now I'm now going to find the t in terms of the x. Alright, so I'll basically divide both sides by pi to the power t times the ln of pi. So my dt will give me 2x dx divided by pi to the power t times the ln of pi. Now I need to look for pi to the power t from this equation, because here I'm converting everything in terms of t to be in terms of x, so I cannot have this right hand side to still be in terms of t again. I already have 2x dx, so I need to eliminate pi to the power t. So back in our substitution, pi to the power t is just equal to x squared plus 1. So replace pi to the power t as x squared plus 1, or in fact we can look for t, because you are going to replace t here with a quantity that is in terms of x. So we can take ln on both sides. Ln of pi to the power t will give us a ln of x squared plus 1. So we can just divide, because t falls down and we have t times the ln of pi equal to the ln of x squared plus 1. So from there, t becomes the ln of x squared plus 1 divided by the ln of pi. That's what I'm going to replace anywhere I find t in my original integral. Okay, now from here, I'm going to replace pi to the power t also with x squared plus 1, and I'm going to have my dt to be equal to 2x dx divided by ln pi, all of that times x squared plus 1. Now we also need to change the bounds of integration, because the original bounds are in terms of t, but our new variable is x, so we need to put the original bounds in terms of x. Now when t is equal to 0, you realize that x squared will be equal to pi to the power 0 minus 1. Pi to the power 0 is 1, because pi is not equal to 0, and 1 minus 1 is 0, so x squared becomes 0, so x is just equal to 0. So the lower bound will still stay at 0. Now when t is equal to plus infinity, you realize that pi to the power t will also give us plus infinity, because pi is bigger than 1. Now plus infinity minus 1 definitely tends to plus infinity. Now to find x, we take the square on both sides, and the square of plus infinity definitely still gives us plus infinity, a big number which is unknown, and it is positive. So the new bounds of integration are the same as the original bounds of integration. So my integral, so if I replace in the integral and simplify, what we are going to have, basically we have to replace x squared with pi to the power t minus 1. We have to replace t with ln of x squared plus 1, all divided by the ln of pi. We have to replace dt with 2x dx divided by the ln of pi times x squared plus 1. When we do that, we are going to get so we are going to have the integral. Now my new bounds of integration still remain as lower bound being 0 and upper bound as plus infinity. Now let us replace bit by bit. All right, now I'm going to replace t with the ln of x squared plus 1 over ln of pi. So here is t, then minus 1. Okay, now in the denominator, the square root of pi to the power t minus 1 is just the square root of x squared, because x squared is pi to the power t minus 1. Now pi to the power t minus 1 is x squared, so replacing it here, we are going to have the ln of x squared. That is it. Now let us go to dt. All right, now let us go to dt. Now in dt, our dt is 2x dx over the ln of pi times x squared plus 1. So I just replace dt with 2x dx over the ln of pi times x squared plus 1. Now basically we have to simplify. All right, so the first thing you realize is that the square root of x squared is just x, because x is already positive. Generally, the square root of x squared is the absolute value of x, which is equal to x if x is in a positive interval or when x is 0, and is minus x if x is in a negative interval or yeah, when x is 0. So the square root of x squared here is going to give us just x, because x is already in a positive interval from 0 to plus infinity. Now the ln of x squared is the same as 2 times the ln of x. So the 2 falling down, meeting with the x from the square root of x squared, we are going to have 2x times the ln of x. Then the rest stay as they are. Now we have to simplify. Let's focus on the numerator here, alright? Because already 2x cancels 2x, as you can see. This 2x here cancels with this 2x. Now when that happens, I'm going to look for the LCM of this numerator. Is going to be the ln of pi, so I just have to multiply. So this numerator simplifies to the ln of x squared plus 1 minus the ln of pi, all that divided by the ln of pi. Then we have to divide it by ln x. Then we multiply it with the x, because 2x has gone away. The x divided by the ln of pi times x squared plus 1. Okay, now you realize that the ln of pi goes to the denominator and meets with this ln of pi to give us 1 over the ln of pi, all that squared. Now our numerator just becomes ln of x squared plus 1 minus the ln of pi, all that now divided by, we have x squared plus 1 times the ln of x, then dx. So we are now going to the second phase of simplification and substitution as well. Okay, so having our integral to be 1 over ln pi all squared times the integral from 0 to plus infinity of this integrand, you already find out that this portion is already out. So it therefore means that this integral we have here is just equal to pi divided by 2. Okay, but the question is how? Now I found out a very trickish substitution I can do, which is going to be very helpful. So what I did was that I let y to be equal to 1 divided by x, okay, because I identified a certain symmetry. Because once I replace y with 1 over x, okay, this x squared plus 1, in fact your x is going to be 1 over y, alright. So x squared will give us 1 over y squared. Then when you're adding 1 to it, you realize that you're going to do the LCM and some things are going to fall off. So that's why I choose to use the substitution y equal to 1 over x. Now if y is equal to 1 over x, this is my new variable, so I have to change everything in terms of x to be in terms of y. Limits of integration, anything in terms of x, and even the derivative dx has now to be converted to dy. Alright, so if y is equal to 1 over x, you realize that x will be equal to 1 over y. Now from here I will differentiate both sides so that I get the x, and if I differentiate 1 over y, I just have negative 1 over y squared dy. Alright, now what we need to do is we need to change the bounds. Okay, now when x is equal to 0, you realize that this is actually 0 from above, because in the interval 0 to plus infinity, x is strictly bigger than 0 or equal to 0. Yeah, because it's in the domain of definition. No, it's not in the domain. X is strictly bigger than 0 because this integrand cannot take 0 as a value. Okay, so this is actually 0 from above, and y being equal to 1 over x, as x tends to 0 from above, y tends to plus infinity, because the denominator will be getting extremely small but positive. Alright, so y goes to plus infinity. Now as x goes to plus infinity, the denominator becomes extremely large, so y tends to 0. Alright, so y is going to begin from plus infinity right up to 0. Now my new integral is going to be, now follow. First of all, let's start with dx. What is dx? Minus 1 over y squared dy. Here is the minus sign outside here, and here is the dy over y squared. Now let us go to x. What is x? 1 over y. So what is x squared? 1 over y squared. So we have to replace. Alright, so we have the ln of 1 over y squared plus 1 minus ln pi, all divided by x squared is 1 over y squared, then plus 1 times the ln of 1 over y. Now look at the way the bounds are. Y begins from plus infinity and ends at 0. Okay, now the next thing we are going to do is we are going to simplify this, the ln of 1 on y squared plus 1. Alright, so simplifying it is very easy. The LCM is y squared, so everything in the interior here just becomes 1 plus y squared, or y squared plus 1, all divided by y squared. Okay, and if you use the property of ln, that is, you have something like the ln of 1 plus y squared, okay, all that divided by y squared. Now, if you use the property of ln, you realize that you're just going to take the ln of the numerator minus the ln of the denominator. So here is the ln of the numerator, okay, and then here we have subtracted with the ln of the denominator. All right, so basically that is what I did there. Okay, so doing that, we have the ln of y squared plus 1 minus the ln of y squared. Then we have to subtract the ln of pi because it was there originally. Now, let us go to the denominator. Let us begin with the ln of 1 on y. The ln of 1 on y is the ln of y to the minus 1, and the minus sign falls down to give us negative times the ln of y. Now, this guy here becomes y squared plus 1 all divided by y squared. All right. Now, we now have to simplify. First of all, I cannot begin from is very absurd to begin from plus infinity to 0. In fact, the lower bound is generally always smaller than the upper bound. So for me to be able to just basically switch the bounds, I'm going to remove one of the negative signs. Okay, so these negatives, if one of the negative signs I find here disappears, then I can easily switch the bounds. That is a property of integrals, of definite integrals. All right, so I'm not going to multiply the two negative signs. I'll basically just switch the bounds. That is, I'll begin with 0 and I'll end at plus infinity. Then I'm going to eliminate one of the signs. All right, now you realize that this y squared here cancels with this y squared here because both of them are in the denominator. So it's possible for them to cancel. All right, when they cancel off, what do we have next? What do we have next to simplify? Ln y squared is the same as 2 ln y. All right, so in essence, x and y are basically dummy variables. Okay, so the integral, in fact this integral is equivalent to this integral where I've just changed the variable from y to x, because they have the same bounds from 0 to plus infinity. Dy becomes the x and so on and so forth. Even you can put any variable of your choice, but I decided to put x because my original I here is in terms of x, and I decided to actually put x because x and y are dummy variables. It works in all cases. Okay, so from there now you're going to see what I'm going to do next. Okay, now look at these two integrals. Both integrals are equal to each other because this was the original I we had, and then by our substitution we realized that this is a new format of the integral I. So I'm just going to add the two integrals, okay, because already you realize that the integrands basically have the same denominator, then they have some similarities in the numerator, but remember there is a negative sign here. So when we add the two integrals, is basically what we are going to do is we are just going to subtract their integrands, okay, because one over ln pi all squared is common in both terms. They have the same bounds of integration, they have the same denominator. So I'm basically going to just subtract this guy and this guy. I'm subtracting because this negative sign here multiplies everything inside here. Okay, so doing that, I plus I, basically we are adding, okay, but like I said, since there's a negative sign here, we'll basically add, but we'll be subtracting because of this negative sign that is here. Remember, I did not say we have to subtract, because if we are subtracting, this guy becomes positive. So we are going to add, but you realize that adding is equivalent to just taking the difference of the integrands. Okay, now 1 over ln pi all squared is common in both terms, so we can factorize it out. When I add I to I get 2i, because this is also I, so we are just adding the two equations. Now 1 over ln pi all squared is common. Now I'm going to be left with, since you have the same bounds of integration, I'll have the integral from 0 to infinity. They have the same denominator, which is x squared plus 1 times ln x. Here is it. Now I'm going to take the ln of x squared plus 1 minus, or actually plus, negative the ln of x squared plus 1, alright, which is just equivalent to the ln of x squared plus 1 minus the ln of x squared plus 1. It vanishes to 0. Now negative ln pi minus negative ln pi is 0, because you're subtracting the same quantity from itself. So nothing in terms of ln x minus negative 2 ln x gives us positive 2 ln x. Now you can send the 2 out of the integral because it is a constant, and then you also realize that there is a common factor in the numerator and the denominator, which is ln x. So at the end of the day, the 2 on the left hand side cancels with the 2 on the right hand side, and you're going to have here 1 over ln pi all squared. Now this integral is an improper integral because we have infinity here, which is not the real number. Okay, so we have to use the limit approach. So this integral is equivalent to the limit as t tends to plus infinity of the integral from 0 to t. I've basically just replaced t with plus infinity, then I'm taking out the limit as t goes to plus infinity, because basically we cannot be replacing infinity into a real valued function, whereas infinity is not a real number. Okay, now you realize that this is a basic integral, okay, and this basic integral is basically tan inverse of x. So we have tan inverse of x from 0 to t, then later we find the limit. Once you replace the upper bound, you're going to have tan inverse of t. Replace the lower bound, we get tan inverse of 0, which is 0. So at the end of the day, we have 1 over ln pi all squared times the limit as t goes to plus infinity of tan inverse of t. But clearly, tan inverse of t goes to 90 degrees, or pi divided by 2, as t goes to plus infinity. In fact, if you punch the tangent of pi over 2, it gives you math error or syntax error because it's a very big value. You can also check the graph. Pi over 2 is tangential, is a vertical asymptote to the graph of tan inverse of t. So punching tan of pi on 2 and getting math error, or in fact a very large value, it therefore means that if we take tan inverse of that very large value, you must get back to pi over 2. The very large value here is positive infinity. So at the end of the day, we can be able to conclude that the integral from 0 to infinity of t minus 1 on this nasty guy here times with respect to t is pi divided by 2 times 1 over the ln of pi, all that squared. Thank you guys for watching, and see you guys in the next video.